So in this webinar, we're going to take a deep dive into the Flow framework. The Flow framework's really what you use to write the core business logic of your Chord app or application that sits on top of the Chorder node. So we're going to spend a lot of time looking at this, and I'll explain to you in detail how it works. So why do we even have the Flow framework? So most distributed ledger technologies use broadcasting of gossip networks. Messaging is simple. So as you can see in the little animation here, data is simply just propagated around the network via gossip network. If there are any duplicate messages, they're just discarded. Messaging is simple to reason about. Disadvantage, though, is unfortunately peers can't control who receives their data, and this is a big disadvantage. And this is why Chord is designed the way it is with point-to-point messaging, so you can specify one recipient or multiple recipients, but it's up to you who sees your data. So it's up to you who you send the data to. We need a way to firstly handle the networking layer. We need a way to handle serialization of the messaging, so the serialization format of the data which you're sending across the wire. We also need to handle the multi-threaded nature of these particular workflows, among other things. So there's a whole bunch of stuff that the Flow framework does for the end developer. So it abstracts a lot of the complexity away from the realities of writing this kind of complex state machine code that you need to manage these multi-party, multi-step workflows. So as I said, with Chorder, peers communicate on a point-to-point basis. So as such, you must specify who your message recipients are. Obviously, in the preceding examples, when we've been talking about an IOU between Alice and Bob, where they both must sign, there has to be an instance in the workflow where Alice is signing a transaction and sending it to Bob so he can inspect it and sign it, and then Bob sends it back with his signature, etc. And this is really what the Flow framework is designed for. So it's designed for this multi-party, multi-step coordination between the two parties such that they can reach consensus about a shared fact. So what does the Flow framework do in a nutshell? It helps you coordinate when, with what, and who with. A very simple example, Alice and Bob again, we can use an animation. If Alice and Bob do want to agree upon an IOU, then what would happen? Alice would first create a new transaction proposal and sign it. She would then send it to Bob with her signature. She needs to sign it because we want to make this transaction proposal immutable, so Bob can see whether it's been changed in transit, for instance, so he can verify it against Alice's signature. Next, Bob inspects the proposal, verifies it, verifies the signature, and then if it's all good, then he would sign it. Then he would send back his signature to Alice. And at this point, both Bob and Alice can record the transaction in their storage service in their vault. And in this example, I've obviously left out the notary, as I have done in previous examples, but on a production Chorder network, you would have a notary service as well, which would sign over the transaction and be the point of finality when that transaction is committed. But we'll discuss that in a later webinar, but for now, just think of flows as a mechanism that facilitates this multi-step communication. In this diagram, you can see that there are three peers that weren't a party to this flow, and thus they didn't receive any of the information. They do not even know that Alice and Bob transacted. They're not a party to any of these messages or transactions. So as we can see, you need some back and forth communication required to commit a transaction proposal, and we obviously need some kind of workflow to manage this, and this is where the Flow framework comes in. But of course, there's more than two parties on the network. There's not just Alice and Bob. There could be thousands, and indeed there could be hundreds of thousands of these workflows happening concurrently, and we need a way to manage those. These flows can have multiple properties that might differ depending on the workflow that is being carried out. So potentially a flow could be fully autonomous, might not require any human interaction, and it might only take a couple of seconds to complete to get signatures from all the required parties and commit the transaction. So taking into account network latency, the flows may only take a couple of seconds to complete. However, others might be very long-lived. They could take hours or days. Maybe there's an employee away sick, so away absent, so it couldn't sign a transaction, and potentially a flow would continue for weeks. And of course, nodes won't stay up all the time. There would be downtime when there's node maintenance, or if there's a problem with the node, then the node would go down and it would be under maintenance. So at this point, any flow that was in operation, it would have to survive a node reboot as well. So how do we manage that? And then the other thing to think about is actually because a lot of the interaction here is via I/O with the flow, so via, I don't know, receiving a message off the network or retrieving some data from a database. So typically what would happen is a flow would be active for a very short period of time, whereby it pulls some data from the database and then composes a message and sends it to another party on the network. Then it will wait for a long period of time to receive a response. And usually when you write code like this, you would take an asynchronous approach. So if anyone's ever used a framework like Node.js, a web server that has one event loop, and with that event loop you can invoke functions which have callbacks that invoke further functions, and they all execute in an asynchronous manner such that none of them block. But the problem with asynchronous code is it tends to look a little terrible. You end up with something like this. Now, this is a bit of a personification of that, but the point stands that you end up with this callback hell situation where the code's quite difficult to reason about. So if here you can see that we have a function whereby we're sending a transaction to a peer, we're expecting a response at some undetermined point in the future, and we're checking the response, and then depending on the result of that, we're handling an error or we're verifying, and then depending on the response there, we may be signing or we enter some error state. So that's typically how an asynchronous workflow would work. But there must be an easier way to write code than this. So this is where the flow framework comes in. Really what we're doing here with the flow framework is creating a mechanism for developers to write their own state machines that control the interaction between the various parties who want to agree upon some shared facts. So you can think of flows as just state machines, and we need essentially a state machine manager that can manage multiple flows at any one time. And it just so happens that we can quite easily do this with lightweight threads called fibers, or perhaps continuations if you know them as continuations. And what we do is we allocate each flow state machine manager to keep track of its current progress. This state machine manager manages the interaction with the network and other services on the node. When the flow is awake, when it's operating, it can access all of the node services, the network, the database, the identity service, for instance. However, when it calls the network, say for example, if it wants to send a message or it's waiting for a message, then what happens is the whole stack that represents the current state of this flow is suspended and serialized to persistent storage. So we say it's been checkpointed, and because the flow is serialized to persistent storage, if a node then fails or restarts, then the flow can just be restarted from the checkpoint. So it's deserialized and the computation will continue where it left off. So how does this work in practice? So let's say we have Alice and Bob and they want to agree upon an IOU. Then you would have Alice that produces a new transaction, allocates Bob as the recipient or the peer. She signs the transaction, creates a payload, and sends it to Bob. When she sends the message to Bob, her fiber or her flow, so the flow is running inside the fiber, is suspended and serialized to disk. So at this point, if the node falls over for any reason, then Alice can continue her flow where she left off when she sent the message to Bob. This is actually fairly simplified, but what would happen is that Bob would send an acknowledgement that he has received the message. If not, then the message would remain on Alice's outbound queue, and she would keep retrying sending the message to Bob until Bob responds with an acknowledgement. At the point where Bob receives the message, then his flow is checkpointed as well. He checks the signature, verifies the transaction, signs the transaction, creates a payload, and sends it back to Alice. His flow is also checkpointed here, and at the point where Alice receives the message, flow is also checkpointed as well. Then at this point, Bob would commit the transaction, Alice would check the signature, verify the transaction, and commit the transaction. So what this allows developers to do is write synchronous code, very similar to this, but the code never actually blocks. When you send a message and you wait for a response, because the flow has been suspended and serialized to disk, some other process can be carried out. So you're not writing code that blocks, and you're not having to deal with multi-threading or any complexities like that. So all of that is abstracted away from the end developer. So this is just to reiterate what I mentioned in the last slide. You can't typically stop and restart code that's written in a blocking manner. So what we actually do is use this framework called Quasar that behind the scenes rewrites the bytecode for this synchronous state machine into an asynchronous state machine. This is essentially what Quasar does. Quasar does all of this for you, so you don't have to think about it. It's quite easy for flow developers to reason about their flows, reason about their business logic. You can use any construct that you'll typically use in a normal program as if it was executing in a single blocking thread. However, that's not what's going on here. You can potentially have hundreds of thousands of flows operating on a machine at any one time. And interestingly, because flows are serialized to disk, you can have more flows in progress than would actually fit in memory as well. So as long as you have persistent storage to store all of your serialized flows, then you could potentially have millions of these operating concurrently. So this is just an easier depiction of what's happening with the flow. We call it the two-party deal flow, and it's one of the stock flows that come with Corda. But actually, it's the flow that's required to agree upon some arbitrary shared fact, for instance, an IOU. And what would typically happen is you would have an initiator and a responder. So flows typically come in pairs, certainly if they require some kind of network communication. And you'd have one initiator that creates a proposal, signs it. You see at the point when the proposal is sent to the other side, Alice's flow is suspended, checkpointed. And then at this point, Bob's flow starts, verifies, signs, commits, sends the signature and the transaction back, and Alice's flow wakes up, inspects, verifies, and commits. So we typically use flow diagrams to represent the business logic of a flow. And it's much easier to approach writing your flows this way with all of the logic in front of you before you start writing them. One pretty cool thing to do with the flow library is subflows. So just like in any procedural programming language, you can call a procedure with a ready-made procedure that does performs some particular algorithm or some function, and you can encapsulate some logic in there that you can recall many times. And you can do the same thing with flows. So if you have a flow that you need to use fairly often, for example, getting a signature from your counterparty, then you can write a flow to do that for you. This way, actually, it allows you to create abstractions and hide a lot of the complex back and forth communication that's required for things to happen. Say, for example, I can write a flow that collects all the required signatures from the counterparties that enter into a multilateral agreement with me. So instead of having to manually write the code to achieve that, we can have a pre-packaged flow readily available that just requires the transaction that we'd like a signature over as a parameter, and it just returns a list of signatures, and it deals with everything for me. I could potentially write many more of these types of flows to improve the experience of flow writing and hide a lot of the complex logic away from the end developer. The end goal is such that writing flows would be quite easy, and you could do it by using some kind of high-level domain-specific language rather than writing Java or Kotlin. And of course, we'd have a flow library and some kind of visual builder that you can use to assemble the logic that comprises your flow. And lastly, a point I'm reiterating here, using subflows rather saves a lot of developer time. So why reinvent the wheel? Certainly if it's already been done, then there's no need to recode it. As I mentioned at the very beginning, flows really contain the core business logic inside your Corda app or your Corda application. They really handle the interaction with the node, error handling, message routing, serialization, all those kinds of things. So the flow is typically where all the logic of your app will be contained. There's an API that's available to developers. The core part of this API is the service hub that provides references to all of the node's transactions. And as well as that, there's some APIs for building transactions, verifying transactions, and assigning transactions and verifying the signatures over transactions. And lastly, there's an API for storing transactions as well. So this is just reiterating the point that flows typically come in pairs. So you'd have an initiator and a responder, and if you want to send data across the network in your flow, then you would need a pair of flows, certainly, because you would need the other side to be able to interpret the message coming off the wire and know which flow to start on their side. However, there can be certain flows that don't require another side, so perhaps you need to use a flow that doesn't necessarily send anything to another party. The flows don't necessarily always need to have two sides to them. Lastly, the third bullet point, because flows are really just classes, JVM bytecode classes, we can subclass them to add custom entity-specific logic. So we can create an abstract flow that requires developers to subclass it and add some specialized business logic for their particular workflow. This is just to reiterate here that flows are lightweight processes, so they're fibers, they're not threads, they're kind of lightweight threads that operate within the user mode, and they're used to coordinate the complex multi-step, multi-peer interactions required for peers to reach consensus about shared facts. So in other words, they comprise the business logic that's required for parties that use this Corda app to reach consensus about some shared fact or some state object.